In last couple of lectures, we are trying to solve the nonlinear Schrodinger equation which governs the pulse propagation on optical fibers. We are taking different regimes, different conditions under which only dispersion is dominant, nonlinearity effects can be neglected. A situation in which the nonlinearity effect will be dominant and the dispersion can be neglected, and when both the effects are present. So, we solved the nonlinear Schrodinger equation for the group velocity dispersion, neglecting the nonlinear effects, and we saw that in that situation the pulse broadening takes place and internally there is a frequency chirp developed because of dispersion. We also saw that for dispersion, the nature of the chirp depends upon whether you are working in the normal dispersion regime or the anomalous dispersion regime. For a wavelength less than 1300 nanometer, where the dispersion is normal, we get a positive chirp. That means the frequency within the pulse increases as a function of time, whereas in the anomalous dispersion regime, the frequency decreases within the pulse as a function of time. So, whether we are working in the anomalous regime or we are working in the normal regime, the pulse broadening always takes place. The spectrum remains same, but different frequencies undergo different phase change. That is what was happening for the group velocity dispersion. In case of nonlinearity, when we solve the nonlinear Schrodinger equation neglecting the dispersion term, then we find that the time envelope does not change, but the spectrum changes. The spectrum broadens, that means new frequencies get generated as the pulse propagates inside the optical fiber. Within the pulse again you have the phase change as a function of time, which leads to change in frequency. So, in this situation also we have a frequency chirping or frequency modulation. However, because of the self phase modulation, the chirp is always positive. That means the frequency always increases as a function of time within the pulse envelope. Then we made a proposition that if we create a situation where the dispersion is anomalous, that means the chirp of the frequency is negative, and if the nonlinearity also is present simultaneously, and if we adjust the parameters in such a way that the chirp created by the nonlinearity is completely cancelled by the chirp created by the dispersion, then the frequency modulation inside the pulse will vanish, and then consequently the pulse broadening also will vanish. Or in other words, if we create a situation where the nonlinear effects cancel the dispersion effect, the pulse can travel on optical fiber without broadening over much longer distances, and that is the situation we called as a soliton. Then we saw also a mechanical analogy what really soliton means, and then we started analyzing what should be the shape of the soliton, how the pulse really evolves, what are the parameters. So, we continued with that analysis. So, we started with a nonlinear Schrodinger equation, and then in that equation then for the soliton we said now the GVD is balanced by the self phase modulation. We define certain normalized parameters. We define the normalized distance, which is normalized with respect to dispersion length. We also define time, which is normalized with respect to the pulse width. We neglect the loss, because as we discussed earlier, in the presence of loss, as the pulse starts propagating, the power in the pulse reduces and the non-linearity becomes weaker and weaker. One can also argue that at any point of time, if the non-linearity becomes weaker than what is required to balance the group velocity dispersion, the pulse will start broadening, and when the pulse starts broadening, the peak power in the pulse will come down. If the peak power comes down, then the non-linearity will further weaken, and then dispersion will further dominate and the pulse will start dominating further. So, at any point in this race of non-linearity and dispersion, if the non-linearity loses to dispersion, then it can never recover back. The pulse will go on broadening. So, for this phenomena to sustain on optical fiber, it is very important that the power level in the pulse should be maintained in such a way that at no point of time the non-linearity loses against dispersion. So, as a simple case to start with, we are taking a lossless case. So, we are assuming that the loss on the optical fiber is neglected, and then the nonlinear Schrodinger equation in terms of these normalized parameters can be written like this, where we have defined this parameter n, which we call as the order of a soliton, which is the ratio of the dispersion length to nonlinearity length. And then we said when LD is equal to L and L, and if the length of the fiber is much larger than LD and L and L, then we get a phenomena what is called the fundamental soliton, which corresponds to n equal to 1. Then to solve this equation here, to eliminate this parameter n, we define another variable, the small u, which is this capital N times the envelope function u, and then by substituting this in the anomalous dispersion regime, when beta 2 is less than 0, that means the sign of beta 2 is minus 1, the nonlinear Schrodinger equation then becomes this. And to solve this equation, then first of all we note that once now the nonlinearity and the dispersion are balanced, then the envelope does not change as a function of distance. So, you have an envelope function which is a function of tau, but does not vary as a function of distance. However, we have a phase function which can vary as a function of time and distance. And if I take this now and substitute into this, you get two equations by separating real and imaginary parts. One equation governs the phase, other equation governs the amplitude, and for phase one can show that the solution to the phase is given by this, which is almost like a wave function kind of behavior. So, you are having a phase constant here, this is a normalized distance, this is the normalized time. So, this quantity is nothing but the frequency shift. So, assuming that the frequency shift is not there in this propagation, one can take delta equal to 0, and then this phase function then can be written as a function of space with this k, which is the constant quantity in this form. So, if I second equation then which we get, which governs the amplitude or the envelope, that is given by this equation now. So, V is the quantity which is the envelope function, which is now not changing as a function of distance, which is governed by this equation. And to solve this equation then, one has to do some trick. So, let us multiply both the side by this quantity 2 times dV by d tau and integrate this as a function of time. So, that is where actually we stopped in our previous lecture, that we have got this equation which tells you the functional form of the envelope, right, which will sustain on the optical fiber without its change in shape. So, by multiplying this we got this quantity here. So, now you will see how the trick will work. So, let us say this is the quantity which is given by some quantity I. So, the I is the integral 2 times dV by d tau d2v by d tau square d tau. I can do the integration by parts. So, this will be 2 times first function d v by d tau to integral of second, which will be d v by d tau minus integral of differential of first. So, that is 2 times d 2 v by d tau square into integral of second. So, which is d v by d tau. Okay. But this quantity, if I look at this quantity, it is same as this quantity. You got 2 times d v by d tau multiplied by d 2 v by d tau square d tau. So, this quantity is nothing but the integral I itself. So, you get here 2 times d v by d tau whole square minus the same integral I. So, this then gives, I can bring this I on this side. So, 2 I is equal to this. So, you get I, which is this integral, that is equal to d v by d tau whole square. So, now things are simple. Now, this integral is this. So, I can substitute into this to get d v by d tau whole square, that is equal to this one, d tau will cancel, you will get d v. So, this is 4 times. So, I get here integral 4 times v k minus v square d v. So, I get this integral is very simple. We can write this, that gives you 2 times k v square minus v to the power 4 plus some constant of integration c. One can then use the boundary conditions to get the value of c. So, if we apply boundary conditions, and that is v is equal to 0 and also d v by d tau is equal to 0 when tau tends to infinity. So, the envelope function is going to 0 and also the slope of that function is going to go to 0. If you apply these boundary conditions on this, then that will give this constant c to be equal to 0. One can also apply the normalizing condition for this, and that is, so normalization gives that v is equal to 1 at tau equal to 0. So, you take a pulse which is a normalized amplitude pulse, and at tau equal to 0, since we are talking about a pulse which is peaking. So, we are saying here your pulse is like this. So, this value is 1 and the slope of this is 0 because we are on the top of this pulse. So, at tau equal to 0, we also have d v by d tau is equal to 0. At the peak. So, if I take this and substitute into this, I can get this constant k, and that k will be equal to 1 upon 2. So, finally, then we got a solution of this equation, which is the envelope is dV by d tau whole square, that is equal to v square minus v to the power 4. One can take square root on both sides to get dV by d tau is equal to v square root 1 minus v square. We can separate the parts to get dV upon v square root 1 minus v square is equal to d tau. So, you can integrate on both sides, and this is the standard integral for which we have the hyperbolic sec inverse, that is equal to tau. So, the solution which you get for this is v is equal to secant hyperbolic tau. Then combining the phase function and the amplitude function, the total solution which you got for the nonlinear Schrodinger equation tau is equal to secant hyperbolic tau e to the power minus j tau by 2. So, what this analysis has given us now is that if we consider a situation of fundamental soliton, that means, if the nonlinearity length is equal to the dispersion length, then the nonlinearity and the dispersion will cancel each other, but this will not happen for any arbitrary function. This perfect cancellation will take place for a pulse which has the secant hyperbolic secant shape, and then it has certain phase term. So, as the things move, this pulse will accumulate a phase as a function of distance, but the envelope will remain intact as it moves, and this shape now is a very special shape, which is a hyperbolic secant shape as a function of time. That is the one which will travel undistorted on the optical fiber. So, this shape now is the fundamental soliton shape. So, fundamental soliton has a very definite shape. It is the hyperbolic secant shape, that is the one for which there is a perfect balance between the nonlinearity and the dispersion, and that is the one which will propagate without any distortion on the optical fiber. So, that is a very interesting analysis. It simply says that if you can create a pulse which has this shape, which is the hyperbolic secant shape, then this pulse can travel on the optical fiber undistorted in the form of the solitonic wave. One may then wonder, how often do we have this kind of solitonic pulses which are actually generated into the system? Let us say I want to transmit some data on the optical fiber. we have the pulses which are of different shapes. It could be simple rectangular pulses, or it could be pulses which will look more like Gaussian pulses or Lorentzian pulses or whatever. But very rarely really we see a shape which is deliberately created, which is a secant, hyperbolic secant shape. So, one can then ask a simple question: if I launch a pulse which does not have a hyperbolic secant shape, then what will happen? Would it form a soliton or would it not form a soliton? Or what will happen to that pulse when it starts propagating? It is very interesting to see there is a non-linear phenomena which takes place in the optical fiber. In the presence of dispersion, it does certain reshaping of the pulse. So, even if the pulse was not hyperbolic secant, but if the non-linearity was good enough, higher than what is really required to form the fundamental soliton, then in the initial phase there is some reshaping of the pulse takes place naturally. So, even if the pulse which is launched inside the optical fiber is not of hyperbolic secant type, there will be some readjustment of the pulse to form this hyperbolic secant shape. Whatever energy does not fit into this shape, that energy may disperse, but a portion of the energy which can get shaped into this hyperbolic secant, that one then does propagate without any modification in shape in the form of a soliton. One would wonder that how often we create the pulses which have a shape which is a hyperbolic secant shape. So, here is a simulation which tells you how the pulse is going to evolve if the launch pulse is not having a shape which is hyperbolic secant. So, what is done here is a pulse which is launched inside the optical fiber is of super Gaussian nature, which is given by this function. So, you see here that if I put m equal to 1, then this is a simple Gaussian kind of distribution. As the m increases, you get the pulse shape which looks more and more flat on the top. So, when m tends to infinity, this pulse essentially becomes a rectangular pulse. So, what the simulation is doing, it is taking a pulse which is of super Gaussian in nature for different values of m and studies how the pulse is going to evolve as it travels on the optical fiber. It is also made sure that the power which is put inside this Gaussian is more than what is needed to form the fundamental soliton. That means, the power in the pulse is taken such that the non-linearity length is smaller compared to the dispersion length. So, this plot here shows now that if you take a pulse which is of super Gaussian nature, initially there is some adjustment in the pulse shape takes place, but finally the pulse evolves into this shape which is a hyperbolic secant shape. So, this simulation shows that it is not important to launch a pulse which has a shape of hyperbolic secant. Even if the pulse shape was not of fundamental soliton nature, but if the non-linearity was strong enough, there is some readjustment of the pulse at the initial stage and the pulse will naturally evolve into this hyperbolic secant shape, which is the shape of the fundamental soliton. Of course, in this process, some part of the energy of the pulse may get distributed and which may not be balanced by the non-linearity. So, that energy will go into the dispersive mode. So, a small fraction of energy actually may get lost into the dispersion, but substantial portion of that energy will go into the formation of the fundamental soliton. So, the simulation is done for different values of m. So, this table shows that if I consider a Gaussian pulse which is corresponds to m equal to 1, you can take a super Gaussian for values of m equal to 3 and then rectangular pulse which is for m equal to infinity. You see that for Gaussian pulse, almost the 99% of the energy gets adjusted into the hyperbolic secant pulse. For the super Gaussian pulse 92% and a rectangular pulse, 86% of the energy essentially gets converted into the solitonic pulse. So, it is not that you have to put too much higher power for nonlinearity to dominate for the formation of this pulse. Even about 15% of change or higher energy, if you put in the fiber, then what is required to form the fundamental soliton, the energy will get molded to form the solitonic wave. So, that is a very interesting simulation which shows that we do not launch the pulses which are of solitonic nature. It is the fiber, the nonlinear effects and the dispersion together, they work in such a way that the pulse shape becomes a solitonic shape. Well, this is the fundamental discussion on the soliton, the first order soliton, which looks secant hyperbolic shape. The question one can ask is that when we are transmitting the data on the communication channel, we are certainly not going to transmit only one pulse. So, the question one can ask is that if we have a train of pulses which are transmitted on the optical fiber, and let us say this train of pulses were in solitonic form. So, you did something initially, some adjustment, and now the pulses which are formed, which are of fundamental solitonic nature. But there are multiple pulses now which are one after another which are going. Would the propagation of these pulses get affected because the presence of multiple pulses? And the answer to this is yes, it does get modified. In fact, this solitonic pulse, which is like a particle, but it behaves more like a charged particle. So, if you are having a particle which has a charge, another particle which has charge, which is another charge, these two particles either can attract or they can repel, depending upon what is the phase or what is the charge on these two particles. So, the like charges they will have repulsion, the opposite charges they will have attraction, and the similar kind of phenomena you see in the solitonic pulses also. So, if you consider the multiple pulses which are propagating, and for just for demonstration purpose, let us say you have these two pulses which are now propagating inside the optical fiber. So, you see this is the time, and initially these are the two Gaussian pulses which were launched, by separated by this distance which is 3 times T naught, where T naught is the standard deviation of the Gaussian pulse. And if the pulse starts traveling now on the optical fiber, these two pulses, you see what happens with these two pulses, something interesting happens. Slowly these are similar identical pulses, so slowly they get attracted towards each other. So, they were separated by this, slowly the separation between them decreases, they almost merge into one pulse, and then again slowly they sort of separate out and they become two pulses. Again after a certain distance they collapse into one, and so on. So, you see that there is some kind of a periodic behavior which takes place on the optical fiber. The two pulses, when they propagate, they become one, after some time they just collapse into one, then they again separate out, after a certain distance they again collapse into one. So, if I look at now the pulses they are traveling, if I look at this location, I see two data pulses as two pulses. If I go to this distance here, the two pulses will not appear like two pulses, these two pulses will appear like one pulse, because they have been collapsed into one. Again at this distance the two pulses will appear like two pulses. So, you see that if you put multiple pulses, then the behavior of this is very different than a single solitary pulse or a single soliton. And this behavior that the pulses collapse into one and then separate out is not very good from the data point of view. So, you have one more simulation here. We said you start with 3 pulses and the separation again is about 3.5 T naught, where T naught is the standard deviation of the pulse. These 3 pulses, they collapse into 2, they collapse into 1, then again they separate out, become 3, then again they collapse 2 into 1 and so on. So, these multiple pulses when you are having, they show this periodic behavior of collapsing different pulses, and this phenomena of merging of pulses and separating out as a function of distance is certainly not a desirable phenomena from the data point of view. Because if the data bits keep on sort of merging into each other and start losing their identity, you will not be able to recover your data. So, this solitonic pulses, though it looks, when the single pulse was going, it can travel for long distance without any distortion and so on. That is not really true if you are transmitting multiple pulses. So, the question one can ask is, if there is some kind of a attraction or repulsion which is going to take place between these pulses, this should depend upon how much separated they are, because we know if there was a single pulse, that means 2 pulses were separated by infinite distance, then there is no possibility of this collapse. So, one can then ask a question, how much we should separate out these pulses so that this effect of attraction or repulsion becomes negligible. And the simulations show that you require about 8 to 10 times T naught separation between 2 pulses to make this effect of attraction or repulsion negligibly small. But what that means is then that the data which we are transmitting is not of this type. We are saying that we should have a pulse which is like this. The second pulse should be separated by a distance which is about, so this is, if this is T naught, the width of this is T naught, the separation between this should be about 10 times T naught. Then the, like that. So, first thing, if you are looking for a solitonic communication, first thing becomes clear that since we are going to talk about these pulses, the data has to be in the form of RZ. The NRZ data, we cannot give you this pulse. If you are getting a train of, let us say, long ones, you will not be able to get this pulse nature into the data. So, the data has to be RZ kind of data for solitonic pulse generation. Second thing, it is clear that the duty cycle of this RZ data has to be only about 10 to 20%, because if it was more than that, then there will be attraction and repulsion between these RZ data pulses. So, we look for duty cycle for this is of the order of about 10%. Only in this situation then we can create the propagation which is a solitonic propagation. Or in other words, what it means is that if I wanted to send the 10 gigabits of data, the pulse width would correspond to 100 gigabits, because the pulse width is going to be about 1/10 of the whatever data rate you are transmitting. So, earlier when we were transmitting the NRZ data, the bandwidth required by the system would be about 2 times, something like that, for the of the data rate. Whereas, now when we are going to transmit this kind of pulses, the bandwidth which is required is order of magnitude higher than the data rate. And that is the reason we will not be able to push the data rate very high, because the total bandwidth required by this is going to be much larger compared to what the data rate is. So, when we are looking at a solitonic communication, it might appear now that since the soliton is a pulse which can travel undistorted over very, very long distance, we can arbitrarily create very narrow pulses and very high speed data, large bandwidth data can be transmitted. But unfortunately, that is not true, because the bandwidth which is required is order of magnitude higher than what the data rate you can transmit. So, that brings us back again to the data rate, maybe typically of the order of about again 10 gigabits, right, which even in the solitonic pulse form, you will not be able to increase the data rate much larger than that. So, that is one issue, that when we are talking about a solitonic communication, then you have to generate the data in the RZ format with a very low duty cycle. Right. That means much larger bandwidth requirement than what the NRZ data normally would require for the normal communication. The second aspect which is again important is that for this to happen, as we mentioned earlier, for the solitonic communication to take place and things to go undistorted, the non-linearity should keep playing role. It should keep dominating over the dispersion. If the non-linearity loses at any point of time, then the dispersion will dominate, non-linearity will become further weaker, and then the game is lost. Then the pulse will go on broadening after that. So, that means at every point we should make sure that the non-linearity length is always smaller than the dispersion length. Now, when you include the loss on the fiber, the non-linearity length will go on increasing because the power level is going to come down. So, we are saying now that if a pulse is launched inside the optical fiber, so we have this optical fiber with the pulse is launched, you launch a pulse in this of such a power that even after loss at the other end of this fiber, the non-linearity length should still remain smaller than the dispersion length. So, if I consider a typical loss of, let us say, 10 dB or something like that on the fiber, even a very modest number, what that means is that the power which is required for the fundamental soliton to sustain at this location, the power at this has to be order of magnitude higher, or non-linearity length now has to be much smaller compared to this length. But if that is the situation at this location, would we get the soliton which is fundamental soliton? And the answer is no. In that situation, the parameter n which we have defined, which is LD by LNL, is greater than 1. So, it could be 2, 3, 4, and depending upon this, then you will have the higher order solitons. And if you do the analysis of the equation, you will see that the higher order soliton do not have a simple shape like hyperbolic secant. For example, if I consider the second order soliton, so if I consider n equal to 2, the shape of the soliton will be given by this, it's 2 times So, you see the shape which you have got now for the second order soliton is extremely complicated shape. So, the data if you want to try to launch, and if the fundamental soliton is not launched, if it is a higher order soliton, then it is not a simple data pulse. The function becomes extremely complicated the function. So, what this situation then means is that if you want to transmit the data in the form of solitonic pulses, and if you have to maintain the soliton here at this location, which is the other end of the optical fiber, I cannot excessively increase the power here to compensate for the loss, because if I just increase the power here, which is just to offset this loss, this power will become excessively large. Then for that power, the instead of fundamental soliton, the higher order soliton will get excited, and which will have a shape which will not be simple pulse like shape. So, I will get a lot of distortion right into the data pulse. So, increasing the power level here, so that the non-linearity keeps dominating over dispersion at every location of the optical fiber, is not the solution to have a sustained solitonic communication on the optical fiber, because here then you get a higher order soliton. So, it becomes apparent then that if you want to make the solitonic communication feasible, workable, then we are not looking for a mechanism which will simply jack up the power at one location. We are looking for a power or looking for a mechanism which will just offset the loss, which will compensate for the loss, so that the power at any location does not become excessively large to excite the higher order soliton. Or in other words, what we are saying is, we are not looking for an amplification process which is lumped at that location. We are looking for some kind of a distributed amplification mechanism which will just keep on compensating for the loss. So, the amplitude of the pulse practically remains constant and it travels on this. So, in no situation the n will go more than 2. It will always remain less than 2, so that the higher order soliton cannot get generated. So, for a solitonic system to become a realizable system, we have to look for a distributed amplification mechanism. So, in a long haul communication link, we cannot really say that periodically we will simply amplify the signal by using some lumped amplifier, and then the soliton will propagate, and when the nonlinearity becomes weak, again we can amplify the signal and so on. We cannot do that, because that is going to create higher order solitonic problems. So, only solution now is to devise a mechanism which gives distributed amplification. And as we have seen earlier, the erbium doped fiber amplifier are the lumped amplifiers. The data travels on optical fiber. When you have a signal to noise ratio problem, at that point we introduce this EDFA, erbium doped fiber amplifier. The signal is amplified, and then again it propagates, attenuates on the optical fiber. Again, when the signal amplitude goes down, we again amplify it. So, periodic amplification we keep doing on the normal optical link. Here we are saying that if we have to use the solitonic communication, then we have to have a mechanism which will keep maintaining the power in the optical pulse. Whatever the loss is, it simply compensates for that loss, and that distributed mechanism is provided by what is called the Raman amplification. So, Raman scattering is another nonlinear effect, and that effect we will discuss later. That effect is used to create the distributed amplification inside the optical fiber. There are many other characteristics of Raman amplification, but from solitonic point of view, the most important thing for Raman amplification is that it gives the distributed amplification. And once you are having a distributed amplification, one can always make sure that at every location the power in the pulse is such that only fundamental soliton is maintained and higher order solitons are not excited. So, a distributed mechanism like Raman amplification is the key word if you wanted to make the solitonic communication possible. Experimentally, people have demonstrated the propagation of soliton inside the optical fiber, not in the real system, but creating the loops of optical fiber and sort of periodically maintaining the power in the optical pulses. The optical solitons have been demonstrated in the laboratory. The optical solitons have to come in real life. So, as the time moves and as the distributed amplification becomes more and more usable in the system, you will see that we will have the propagation, high speed data communication which inside the fiber will be in the solitonic form. So, let me summarize what we have done. We are looking at different nonlinear effects and dispersion effects on the optical fiber. So, we made a simple formulation of the wave equation, approximated it, linearized it, and we got an equation what is called a nonlinear Schrodinger equation, which gives the evolution of a pulse on the optical fiber in the presence of dispersion and nonlinearity. We saw in the dispersion domain, the pulse broadens, the spectrum remains intact. In the nonlinearity domain, which is self phase modulation, the pulse envelope remains intact, the spectrum broadens. When you are having both of these two together, then we have a phenomena what is called a soliton, and in this case the pulse neither broadens nor contracts, it does not get internally frequency modulated. So, this phenomena travels like a particle, but then we saw that if you have multiple solitons traveling next to each other, then they behave like charged particle form. That means, they have a behavior the charged particles have, they have a force of attraction, repulsion. So, when the multiple pulses start traveling in the form of solitons, they show collapse of two pulses, against separation, some periodic behavior, which is not very attractive. So, then we saw that to have multiple pulses transmit in the solitonic form, we have to create pulses which have very low duty cycle. They are in the RZ format with low duty cycle, so that the attractive or repulsive force between the two solitons becomes negligibly small, and these pulses can keep traveling in the form of solitonic pulses. Then we also saw that to make it more practically realizable, the distributed amplification is most important, because the lumped amplification, if we use for periodically for compensating for the fiber loss, it will create possibility of higher order solitons which are not simple in shape. So, by using distributed amplification, the power level inside the soliton can be maintained, and then the pulse can propagate in a sustained fashion in the form of fundamental soliton. So, there are practical demonstrations of this, but solitonic communication still has to become a reality in real life, but as the time moves, we will see the solitonic communication happening a reality in future.